Section: Introduction. In this section, we discuss the significant impact of large language models, LLMs, on natural language processing, NLP, and how this has led to the creation of multimodal large language models, MLLMs, that combine language and visual understanding. We recognize that enhancing MLLMs relies on two main strategies: improving model architectures and the quality of datasets. Most leading MLLMs follow a two-step process, starting with pre-training on a large number of image-text pairs to align modalities, followed by fine-tuning to boost visual question answering, VQA, skills using specialized datasets. We emphasize that the quality of pre-training datasets is crucial for MLLM's performance in visual tasks, while the quality of visual instruction tuning datasets is vital for their overall effectiveness in VQA and other applications. Recent studies have successfully incorporated object detection and optical character recognition (OCR) datasets, like RefCoco and Visual Genome, which have improved MLLM's abilities in detailed image tasks. To further advance this field, we introduce a new dataset called Img-Diff, which consists of pairs of very similar images with slight changes. This dataset encourages MLLMs to analyze paired images and identify differences in specific areas, enhancing their ability to recognize fine details. After creating our dataset, we integrated it into the original visual instruction tuning datasets of LLAVA 1.5 and MGM, followed by fine-tuning these models and evaluating their performance on various benchmarks. Our results show that after fine-tuning with Img-Diff, LLAVA 1.5 to 7b and MGM 7b significantly improved their performance on image difference benchmarks, even surpassing state-of-the-art models like GPT-4v and Gemini. Additionally, these models showed overall improvements across many recognized MLLM benchmarks, with an average score increase of up to 3.06%, highlighting the effectiveness of our dataset in enhancing MLLM's image recognition skills. We also assessed the diversity and quality of our dataset, ensuring it includes a wide range of object categories and variability. Through careful manual labeling, we confirmed its high quality. We conducted studies to explore the impact of different filtering intensities and examined an alternative method for creating image difference data focused on object removal, yielding valuable insights for contrastive data synthesis. In summary, we present a new data synthesis method and the Img-Diff dataset, which features pairs of similar images created through object replacement. We performed visual instruction tuning on LLAVA 1.5 to 7b and MGM 7b using our dataset and rigorously evaluated the model's performance on various benchmarks, demonstrating significant improvements. We also provide a thorough evaluation of our dataset's diversity and quality, identifying optimal filtering thresholds through ablation studies. To support ongoing research, we have made our dataset and code available online, encouraging further exploration in MLLM datasets and image difference methodologies. Section Summary. In this section, we discuss the advancements in multimodal large language models, MLLMs, and introduce our novel Img-Diff dataset, which consists of pairs of similar images with subtle differences to enhance MLLM's fine-grained image recognition and visual question answering capabilities. We demonstrate that fine-tuning models like LLAVA 1.5 and MGM with our dataset leads to significant performance improvements on various benchmarks, underscoring the importance of high-quality visual instruction tuning data. Section: Datasets on image differences. In this section, we discuss datasets that focus on image differences, which usually consist of pairs of similar images along with descriptions of their differences. For example, the Spot the Diff dataset includes pairs of street scenes taken at different times, while the CLEVR change dataset shows variations of geometric objects against a plain background. The Birds to Words dataset highlights subtle differences among bird species in their natural environments. The Image Edit Request dataset pairs edited images with their originals and describes the changes made. Some studies have utilized advancements in image editing technologies to create datasets centered on image differences, such as Instruct Pix2 Pix, which uses a specific image editing technique to generate similar image pairs and employs a language model to create descriptive captions. Our approach is similar, as we also use the prompt-to-prompt technique with the Stable Diffusion XL model to generate pairs of similar images. However, we add multiple filtering stages to ensure high data quality, focusing on generating captions that describe specific areas of difference rather than the entire image for better accuracy. Next, we explore image difference captioning, IDC, a specialized area of image captioning that emphasizes subtle variations between images instead of just identifying common objects. The initial work in IDC, Spot the Diff, suggests areas of change and uses a specific type of decoder to create captions for these variations. Other models, like Duda and Vard, use different techniques to analyze image differences at a deeper level. With the rise of multi-layer language models, MLLMs, Vixen is the first to apply these models to IDC tasks, extracting features from outputs and generating captions. Our dataset is tailored for MLLMs, constructed based on visual instruction tuning formats from popular MLLMs, paving a new path for enhancing MLLMs through a data-centric approach. We also note that contrastive learning methods have greatly improved how vision language models understand image-text relationships. These methods involve pairing images and texts, helping models distinguish between matching and non-matching pairs. Our method applies these principles to create MLLM image-text data, focusing on object replacement between image pairs to help MLLMs recognize fine-grained differences. The process of generating this object replacement data consists of three parts. First, we create similar image pairs with only object replacements. Second, we extract regions with differences. And third, we generate descriptive text for these areas and create question-answer pairs. This process involves careful model selection and filtering, which we detail in the appendix. Before generating our Img-Diff data, we first create numerous pairs of similar images. We follow a process that involves object replacement in images, inspired by Instruct Pix2 Pix but using the more advanced Stable Diffusion XL for better image quality. We start by gathering 118,000 image captions from MS Coco, which are focused on real photos. Then, we use the language model VICUNA 1.5 to 13b to replace objects in these captions. The prompt we use instructs the model to replace one object in a given sentence. Finally, we generate image pairs based on these new captions using the Stable Diffusion XL model and the prompt-to-prompt technique, ensuring that only a few objects are replaced in the images. Section Summary. In this section, we describe our approach to generating datasets focused on image differences, utilizing advanced generative models like Stable Diffusion XL to create pairs of similar images with specific object replacements. We also outline our method for image difference captioning, IDC, which emphasizes fine-grained variations and employs contrastive learning principles to enhance the capabilities of multimodal language models, MLLMs, in recognizing and describing these differences. Section Overview. In this section, we describe the difference area generator, which helps us find differences between pairs of images. While object detection models can identify objects, they often have a limited range of categories. To address this, we created the difference area generator, which uses segmentation and image similarity checks to broaden the range of detectable objects and enhance dataset diversity. Our process begins with the image similarity filter, which helps us find image pairs that are similar but not identical. We then use FastSAM for image segmentation, cropping the images based on the bounding box data we obtain. After cropping, we apply the image text matching filter to check for valid objects in the sub-images. Finally, we use the difference detector to confirm differences between the bounding box areas of the image pairs and apply IOU filtering to eliminate overlapping boxes, resulting in valid bounding box information. The image similarity filter assesses how similar two images are by extracting features and calculating cosine similarity. If the similarity score meets our threshold, we consider the pair valid. We use this filter twice. First, to ensure the images are similar before segmentation, and second, to filter the cropped sub-images for differences. Next, the image text matching filter checks if an image contains valid objects by comparing image features with textual descriptions. If the matching score is acceptable, we consider the objects valid. This filter is applied after cropping to confirm the presence of valid objects in the sub-images. In the final stage, the difference detector checks for differences in the bounding box regions. We crop sub-images from both images based on the bounding box and filter them through the image similarity filter. A bounding box is deemed effective only if the differences are significant. We then use the IOU method to remove overlapping boxes, keeping only those with notable differences. After identifying valid bounding box regions, we use the difference captions generator to create captions that describe the content of these areas, focusing on one bounding box at a time. This approach allows us to address multiple differences in an image pair more accurately. We highlight specific regions with red boxes and generate targeted captions. The process consists of two stages. In stage 1, we select the 5 bounding box regions with the least similarity and describe them using the MLLM next. We then apply 2 filters, the image text matching filter to check for content accuracy and the caption similarity filter to assess differences between captions. This filtering yields valid bounding boxes and captions for the next stage. The caption similarity filter determines if 2 captions for a bounding box are different by calculating their cosine similarity. If the score is low, we consider the captions distinct. In stage 2, we highlight the valid bounding boxes with red boxes in the images. We then provide the MLLM next with the captions and ask it to describe the differences based on the highlighted images. This process results in the final difference captions for the bounding boxes in the image pairs. Section Summary. In this section, we describe the difference area generator, which identifies object differences in image pairs by using segmentation and image similarity comparisons. We employ various filters, including the image similarity filter and the image text matching filter, to ensure valid bounding boxes and generate targeted difference captions for specific regions, enhancing the accuracy of our object detection process. Section: Data Statistics. In this section, we generate 118,000 pairs of similar images using captions from the MSCOCO dataset. We then apply the image similarity filter to narrow this down to 38,533 highly similar image pairs. Next, we utilize the difference area generator to create 117,779 valid bounding box details, allowing for a maximum of 5 bounding boxes per image pair. Finally, we use the difference captions generator to produce 12,688 high-quality instances of object replacement. To assess the effectiveness of our Img-Diff dataset, we fine-tune the popular MLLMs LLAVA 1.5 and MGM with our dataset and evaluate them against various benchmarks for image differences and MLLMs. The image difference benchmarks we use include MMVP, Spot the Diff, and Image Edit Request. For fine-tuning, we combine our data with the original visual instruction tuning datasets of LLAVA 1.5 and MGM, and we conduct additional fine-tuning for 2 epochs using the training data from the benchmarks. In our tables, RP stands for Object Replacement Data. We select several state-of-the-art models for comparison based on the original papers and recent studies on image difference captioning. Regarding the MMVP benchmark, which evaluates the visual capabilities of MLLMs, we find that it focuses on pairs of images that are similar in features but differ in content. The questions in MMVP are closely related to our dataset, emphasizing the differences between similar images. Our results show that fine-tuning LLAVA 1.5 to 7b and MGM 7b with our object replacement data significantly enhances their performance on the MMVP benchmark. After fine-tuning, LLAVA 1.5 to 7b outperforms LLAVA 1.5 to 13b, and the fine-tuned MGM 7b shows a notable score increase, even surpassing the scores of top models like GPT-4v and Gemini. This indicates that our dataset improves the MLLM's ability to differentiate between images with similar features but different content. For the Spot the Diff benchmark, which consists of street view images captured at different times, we evaluate our fine-tuned MLLMs using metrics like Blue, Meteor, Cider-D, and Rouge-L. Our findings reveal that after fine-tuning with our object replacement data, both LLAVA 1.5 to 7b and MGM-7b show significant performance gains, highlighting our dataset's effectiveness in detecting subtle differences between similar images. In the image editing request benchmark, which focuses on image editing tasks, we evaluate our models by requiring them to generate descriptions of transformations between image pairs. Our results indicate that both LLAVA 1.5 to 7b and MGM-7b initially perform well, but after incorporating our object replacement data for further fine-tuning, they achieve even higher scores, demonstrating improved abilities to recognize and describe differences in image pairs. Lastly, we assess our Img-Diff dataset's impact on the overall capabilities of MLLMs using various benchmarks, including VQA-V2 and GQA for visual question answering, and others for testing reasoning and localization abilities. Our results show that after fine-tuning with our dataset, LLAVA 1.5 to 7b experiences an average performance increase of 3.06% across all benchmarks, while MGM-7b sees a 1.28% improvement. These enhancements indicate that the fine-tuned MLLMs not only improve their ability to discern differences but also enhance their overall visual capabilities, making them more effective in VQA tasks. Section Summary. In this section, we generated 118K pairs of similar images and filtered them to create a dataset that significantly enhances the performance of MLLMs like LLAVA 1.5 and MGM on various benchmarks, including MMVP, Spot the Diff, and Image Editing Request, demonstrating improved capabilities in distinguishing subtle image differences and overall visual understanding. Our fine-tuning process led to notable performance gains, with LLAVA 1.5 to 7b achieving new state-of-the-art scores across these tasks. Section: Ablation Studies. In this section, we explore how different filtering thresholds affect the performance of our data. We set various thresholds and create multiple versions of our dataset. We then fine-tune different versions of LLAVA 1.5 to 7b using these datasets and assess their performance on standard MLLM benchmarks. We refer to the filtering thresholds as follows: is for image similarity, BITM for bounding box image text matching, CS for caption similarity, and CITM for captions image text matching. From our evaluations, we noticed that adjusting these threshold from 0.9 to 0.98 to 0.85 to 0.98 in Model 3 leads to a significant drop in performance, highlighting the importance of image pair similarity for data quality. When similarity is low, the data generation can introduce more irrelevant areas, making the results less effective. For BITM, Model 2 raises the threshold to retain only bounding boxes likely to contain valid objects, resulting in slight performance improvements. However, when Model 5 removes BITM filtering, allowing any object difference to count as valid, we see a significant decline in performance. This indicates that maintaining a higher BITM filtering intensity is crucial for better results. In terms of CS and CITM, Model 3 increases both thresholds compared to Model 2. This means we filter out more similar captions and enhance the alignment between captions and objects. The performance improves significantly with these adjustments. Our findings suggest that stronger filtering leads to better dataset effectiveness, but we opt for Model 3 to ensure we still have enough instances. To evaluate the quality of our Img-Diff dataset, we randomly select 1,000 instances of object replacement data and have professional annotators assess them based on 3 metrics. The first metric, bounding box difference, checks for differences between sub-images, scoring them as high, medium, or low based on object similarity. The second metric, content caption accuracy, evaluates if the captions accurately describe the sub-images. The third metric, difference caption accuracy, assesses if the final captions correctly describe the differences between image pairs. Our results show that our dataset is of high quality. For the bounding box difference, only 4.5% are rated low, with nearly 80% showing significant differences. In content caption accuracy, 80.1% of pairs are accurately described, confirming the effectiveness of our labeling and filtering strategies. For difference caption accuracy, over 70% of descriptions are accurate, with some errors only in feature labeling, further validating our caption generation approach. Section Summary. In this section, we investigate the effects of various filtering thresholds on our dataset's performance by fine-tuning the MLLAVA 1.5 to 7b model with different configurations, revealing that higher filtering intensities generally enhance model performance and data quality. Our evaluation of the Img-Diff dataset shows high accuracy in bounding box differences and caption descriptions, indicating the effectiveness of our filtering strategy and data generation process. Section: Data diversity. In this section, we examine the importance of data diversity in our dataset. We analyze the valid object nouns found in the captions of our image pairs to evaluate the diversity of our object replacement data. We count the total number of object categories, unique object replacement pairs, and how often each object category appears. Our findings, shown in Table 0.65, reveal that our dataset covers 1,203 object categories, representing a wide range of real-life objects. An object replacement pair consists of the names of the replaced and replacing objects. We have 3,680 unique pairs, with an average of 3.4 occurrences per pair. Overall, there are 25,288 occurrences of object categories, averaging 21.02 occurrences per category. To assess how well our dataset includes common object categories, we compare it with the Object 365 dataset. We find that each object category from Object 365 appears about 36.07 times in our dataset, totaling 13,164 occurrences, which is around 52.06% of all occurrences. This shows that our dataset contains many common object categories, ensuring they appear frequently. Additionally, nearly half of our dataset consists of less common object categories, highlighting its broad coverage and high diversity. Next, we explore object removal. We create a new dataset that focuses on identifying the presence or absence of objects. This prompts MLLMs to determine which image in a pair contains a specific object. Upon evaluating this new dataset, we observe that the performance of MLLAVA 1.5 to 7b improved by 3.91%, while MGM7b's improvement was 1.1%. These results suggest that if the fine-tuning data for MLLMs is limited and lacks information on object presence, using object removal data could be a viable option for data augmentation. More details about the object removal data can be found in the appendix.